Math 1314, Tyler Junior College, Section 3.5, Rational Functions, identifying horizontal asymptotes. In the previous two videos, we discovered what causes vertical asymptotes versus holes in graphs and developed a technique for locating both. In this video, we're going to discover a technique for identifying horizontal asymptotes and then try to refine it so that we can get the answer with as little work as possible. Two things. Number one, just a reminder of what makes a horizontal line a horizontal asymptote relative to arrow notation. The line y equals c is a horizontal asymptote of the function f of x if that function approaches c as x approaches either infinity or negative infinity. Translation: if you go really far right or left, your graph flattens out to that line. Remember, horizontal asymptotes' purpose are to describe the end behavior of a rational function's graph, which may rise or fall, but oftentimes they don't. They settle down to a certain value. Now, how are we going to find that value? Well, first notice these three functions I've set up are fairly identical, except in one characteristic. On each of them, the degree of the numerator is different. F of x equals 5x plus 1 over 2x squared plus 1. Degree in the numerator is 1. G of x equals 5x squared plus 1 over 2x squared minus 1. Degree of the numerator is 2. H of x equals 5x cubed plus 1 over 2x squared plus 1. Degree of the numerator is 3. Other than that, they're identical. Now, how are we going to find out what these function values approach as x approaches infinity or negative infinity? The answer is we're going to take advantage of a trick. Now, this trick is really based in calculus, but I think it's simple enough that we can follow it. The trick is for any positive power n greater than 0, as x approaches either infinity or negative infinity, the reciprocal of x to that power approaches 0. And this is easy to explain. The reason the power has to be positive is because if it were negative, exponent rules would put it on the top of the fraction. So it's going to stay down there at the bottom. If you have any power and start putting in progressively larger values of x, this denominator will keep getting larger and larger and larger. How fast it increases depends upon the size of the power. But regardless, the denominator of this fraction will continue to grow as x gets closer to infinity or negative infinity. But in a fraction, if the numerator is static, in this case it stays 1, and the denominator is getting larger, then your fraction is collapsing and getting smaller. How small? As close to 0 as we want. So we're going to take advantage of the concept that the reciprocal of a positive power of x will vanish to 0 if x is allowed to get larger and larger and larger, either positively or negatively. But how can we use that here? Nowhere in any of these functions do we have 1 over x to a power. We got an x, we got an x to the power down here, but nowhere there's a 1 over. Well, we're going to use another trick. The trick is to multiply both sides by the reciprocal of the largest power in the denominator. Let me say that again, that's a lot of words. The trick is to multiply both sides of the fraction by the reciprocal of the largest power in the denominator. Now in all of these, the largest power in the denominator is x squared. So what this means on all of these is we are going to multiply both sides of this fraction by the reciprocal of x squared. 1 over x squared, 1 over x squared. What a mess it's going to make, but it's going to clean up real nice. This, of course, invokes the distributive property on both sides of these functions. So let's see what happens. Distributing the 1 over x squared to the plus 1 is easy. 1 times anything is itself. But if we distribute the 1 over x squared to the 5x, and think of the 5x as 5x over 1, and multiply, we get 5x over x squared. But wait a second. 5x over x squared can reduce by an x. So let's go ahead and cancel the x on top with one of the x's on bottom, and now the numerator is 5 over x plus 1 over x squared. In the denominator, we kind of get the same thing. On the back end of the distribution, we get negative 1 times 1 over x squared, which is negative 1 over x squared. But on the front end, the 1 over x squared times the 2x squared, the x squareds would end up canceling, leaving me 2 times 1, which is 2. Oh, and by the way, I need to make one more clarification over here. This numerator doesn't have to be 1. It can be any constant. We'll call it k. Because as long as the numerator is not growing, staying put, but the denominator is getting larger, the whole fraction collapses. So what does this approach? Well, what does this approach as x approaches infinity or negative infinity? Well, according to this trick, any fraction of this form, a number over a power of x, will approach 0. So this fraction is the correct form, a constant over a power of x, first power of x. It approaches 0. This fraction is of the correct form, a number over a power of x, so it approaches 0. That's just 2. And this fraction is the correct form. It approaches 0. So 0 plus 0 is 0, 2 minus 0 is 2, and therefore our horizontal asymptote is y equals 0. Remember, the horizontal asymptote is the value that the function approaches as x approaches infinity or negative infinity. And if we can trick out the function to get some fractions that look like this, they shrink down and collapse to 0. Let's try the second one. Oh, by the way, there's a shorter way to do this. We're going to figure it out first. Again, the trick to the setup is to multiply by the reciprocal of the largest power in the denominator, which is still x squared, so let's multiply both sides by 1 over x squared. And think about what we would get. Again, the 1 and the negative 1, those are predictable. Those are easy to multiply by. But what would happen with the 5x squared? The 5x squared times the 1 over x squared, the x squareds would cancel, leaving just a 5. And the same thing would happen here. The x squareds would cancel, leaving just a 2. Now who's approaching 0? Remember, any fraction of this form will collapse to 0 as the x gets larger and larger. Here's a fraction of that form. It will collapse to 0. Oh, the 5 is just a 5, by the way. And the 2 is just a 2. And this fraction collapses to 0. So we get 5 halves, 5 over 2, and therefore the horizontal asymptote is y equals 5 over 2. Okay? What about the last one? We did the same thing on the last one. The denominator down here is doing the same thing every time, so there's no need to discuss that again. We get 2 minus 1 over x squared. Oh, and by the way, the reason we use the reciprocal of the largest power in the denominator, if we use a bigger power than the largest power, everything on top collapses to, everything collapses to 0. So if that happens in the denominator, we're in trouble. So by using the largest power in the denominator, we're preventing the case where all the terms go to 0 and therefore the denominator goes to 0. So back to this, if we multiply by 1 over x squared, again, the plus 1 on the top gets multiplied, that's easy. But the 5x cubed times 1 over x squared, if we put them on top of each other, 2 of the x's cancel, but there's still one left on top. If I put the 5x cubed over the x squared, 2 of the x's cancel, but there's still one left on the top. So this fraction, the first term on the top becomes 5x. Now why is that a problem? Well, think about what x is doing. X is approaching infinity or negative infinity. Let's just say for the sake of discussion that x is approaching infinity for this one. The 2 stays put, this fraction goes to 0, this fraction goes to 0, but when x gets real closer to infinity, what's 5x doing? 5x is getting closer to infinity 5 times faster. So this doesn't stay 5, this doesn't collapse to 0, this also goes to infinity. Well, loosely speaking, infinity plus 0 is infinity, 2 minus 0 is 2, and infinity divided by 2 is infinity, again, very loosely speaking, because something's infinitely large, cut it in half and it's still infinitely large. So what does this mean about the horizontal asymptote? Well, keep in mind that we're describing in behavior. We're describing what happens to the y value as the x value does something. As the x value approaches infinity, so does the y value. This would tell me that the right hand rises, but we're not going to go that far. We're just going to say, therefore, there is no horizontal asymptote, because the y value is not settling down or approaching a finite value as x gets closer to infinity, unlike these two where the y was approaching a finite value. So there are circumstances under which there will be no horizontal asymptote. Oh, and by the way, if we had said x approaches negative infinity, 5 times negative infinity is negative infinity. This would have been negative infinity. So as we go forever left, the graph goes forever down and the left hand falls. Again, you're not going to be really held accountable for saying left rises, left falls, right falls in the event that there is not a horizontal asymptote. You're simply going to be responsible for saying there is not a horizontal asymptote. Now, if you're worried about, oh my gosh, where did all that algebra out of nowhere come from? I can't do that. Don't panic, because there is a much easier way to get the answer to what is your horizontal asymptote. I will give you a hint though, it has to do with degrees on both the numerator and the denominator. I want you to think about why this became 0. This became 0 because the top was 0, because all this became 0, because both of these became fractions, because this power was bigger than any of these. This became 5 halves because there was a 5 and a 2 here, because there was a 5 and a 2 here, because these numbers lost all their x's because these powers matched. This became infinitely large because we had a non-fraction with an x on the top, because we had a bigger power on the top than the reciprocal of the one that we used from the bottom. So inside of all that mess is a very easy way to not only decide, do you have a horizontal asymptote, but locate it almost instantly. You'll see in the next video.